let's have a look at what happened in the 19th century. And, well, Yingfei, please shut down your microphone. Yes, thank you. So, well, what do we have in the 19th century? First of all, we have Mendeleev table of elements, okay? Mendeleev table of elements. This was a great Mendeleev table of elements, periodic table it's called, yeah? Okay, of chemical elements. It was formulated in 1869 elements. So it's 1869, okay? So what was characteristic of this idea of a chemical element? That it cannot be changed, that it is unchangeable, or so we can even say eternal. So nothing can happen with this element. So this, how to say, hypothesis or this premise was, I would say, challenged by the uh, by the discovery of radioactivity. Radioactivity. So, Ahmed, please shut down your microphone because we hear some noise.
Okay, okay,
So,
okay.
yes, and also Jeffrey, yes. So now, let us look at this one more attentively. Maybe Maria Zaychinoka can help us. So what was revolutionary in the discovery of radioactivity? And by whom was it discovered? Maria. Maria Zaychinoka. You left already.
Yes, yes, yes,
Yes.
yes.
Answer my question.
Oh,
What was revolutionary in the discovery of radioactivity, and how radioactivity disproved the idea of the unchangeable nature of chemical elements?
maybe because it was figured out that different elements are able to be like partitioned, like atoms could be just partitioned into smaller parts, which would represent other elements.
Very good. So this was called radioactive decay or atomic fission or nuclear fission, yes. So, well, the example was what happened with radium, okay? This new element, which was found by Marie Curie, radioactivity and then radium, okay? Well, why was it called radium? What happened? Who can answer me? Radium. Why was it called radium?
Because it
What is,
shines
yes,
in the darkness.
yes, radius is in Latin ray of light. So radium is an element that emitted rays, okay? So
Mm.
these rays affected the photo, well, the photo paper or photo plate, you understand? So if that's how it was found, this radioactivity, that the well uh, that some how to say, chemical compounds containing uranium were placed by, well, just on the some photo, I would say photo table or photo paper. And after that, there was this photo paper was somehow um, mm, uh, well, we see, well, there appeared some, uh, well, some image of these crystals containing uranium. So the only explanation is that through the uh, through the packet in which it was enveloped, there come some rays which that penetrate even package and come to this photo paper or photo tablet and somehow expose it, yes, with light. So there was some image on that. So this was just the beginning, and then followed long investigations which led uh, mm, to the discovery of atomic or nuclear reactions, I would better say. Well, at that time, they couldn't be called nuclear reactions because there was not nuclear reactions. Mm, uh, because at that time nobody knew what the atom looks like. And there were even physicists which doubted the existence of atoms themselves. So, so all these our like revolutionary changes in our knowledge of matter developed at the end of the 19th and the beginning of the 20th century. So it started with the first experiments on radioactivity, which took place in France starting from 1896. Okay, and the heroes are Maria Curie. Well, who knows something about her? Maybe um,
He is
also,
the first test tube baby.
yes, she had two daughters, Eva and Irene.
I
Both were,
think she
well,
was from Poland also.
yes,
Got
her,
the
And
family Nobel Prizes.
yes,
and
I think
if
it
I remember correctly, she got two Nobel Prizes.
two Nobel Prizes, one
Yes.
in chemistry
One
and
for
one
physics
in,
and one in chemistry.
yes, Sklodowska. So her Sklodowska. So her maiden surname was Sklodowska. Curie was the family name of her husband, Pierre
And
Curie. He was
yeah,
also
she also got like Nobel Prizes if I remember correctly.
so two. This first of all, she was a woman, and I think it is the first woman in our lectures. Yes, uh, before there were only men. This is important just to point out or to set an underline. And the second is that she received two Nobel Prizes, which is very rare. There are some other examples, but not very many. Okay, not numerous. And also, what is important is that one of the elements which she discovered, she called polonium. Polonium, which she named after her native country, Poland. Well, at that time, Poland didn't exist as a country. It was divided between Russia, Germany, and Austria. So Austro-Hungarian Empire. So there was no Poland at all, but there was a Polish nation which spoke Polish language and had uh, 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 brilliant history. You understand, and national identity, and so for her, it was very important. That's why she called this new discovered element discovered by her polonium. Well, polonium was like radium, was very radioactive and poisonous for ill for her health. So she developed, while experimenting with these new substances, she developed disease. Well, we call it mm,
Leukemia.
yes, well, something like that. We call it chronic radio disease caused by radioactivity, okay? Exposure to radioactivity. Well, we can call it also ray disease, in Russian, but I'm not sure that there is such expression in England. Ray disease. Well, you can look it. Uh, in Russian, Maria Zaychenoko will understand me, it's лучевая болезнь, okay? Well, who can help me with the
What is the
Huh?
what is the hint?
No, if you are exposed to radioactivity, what can you develop? What kind of a disease?
Cancer.
Cancer, yes, but
Cancer.
Huh?
Cancer.
We can create
Cancer.
cancer, cardiovascular diseases.
It is. I think it's in English. It's called like radiation sickness. Just like.
Radiation sickness, yes.
Yeah. Well, it probably is called like that, but I don't know correctly. In like, it's if you are exposed to in a short period of time a very large amount of radiation. But I think she developed cancer in the end of her life of just
At the
carrying
end,
around
yes.
like
But
radioactive
she,
matters.
uh, radioactive uh, radioactive sickness, yes. Maybe. Well, so there are some ideas, but well, before cancer, because if it was cancer at the beginning, so she will just die, but she lived for a long time. She lived and she gave birth to two daughters, so somehow she managed to live. Maybe Maria Молчанова knows what is лучевая болезнь in English, ray disease.
I
It's
told Chad that the radioactive sickness, isn't it the
Yes,
answer?
yes, radioactive sickness. Yes, it's normal for that. Yes.
Yes.
Okay. So so here is there also some revolutionary idea, because there was no, well, of course there was some radioactive sickness which was developed, um, radiation sickness, okay, not radioactive sickness, but radiation sickness, yes. So it was, of course, developed by those who were exposed to uranium salts, for example, while because uranium was somehow, well, uh, there were some uranium mines, and so people who worked in the mines, of course, they were exposed to radioactivity, but they didn't know that. Also, perhaps people living in the far north were also exposed to radioactivity due to activity like cosmic radiation, okay, in the far north. But also they didn't know anything about that. So people were quite ignorant of this phenomenon of radioactivity. So that's why we can call it a kind of a revolution in our um, uh, how to say concepts of matter and our concepts of the world. Also, unchangeable nature of chemical elements was like disproved. Now, starting from the experiments of Marie Curie, everybody knew that chemical elements are not, some of them are not stable, and then they can change into each other, okay? So this is we can say radioactive decay, or we can say nuclear fission, or then well, it was only the beginning. The idea of atomic nucleus was not yet formulated. It was formulated by another physicist, Rutherford, in England. Well, more or less at the same time, in the beginning of the 20th century. So Rutherford started with his collaborators, um, uh, uh, like Heiger or Geiger, we can say. He started experiments with golden foils, thin golden foils, which he exposed to alpha particle radiation. What is that alpha particle? This is alpha particle. This is a question which are usually uh, who wants to answer what is alpha particle?
If I remember correctly, it's just like the nucleus of like helium atoms, like helium without
Helium, yes.
electrons. Yes.
Of helium, of
I think it is
helium.
positive particles, which has a positive cation.
Yes, it is. They are positive, and they consist of two protons
Two
and two
protons, two neutrons.
Yes, and so the charge is two positive electron charge. Okay, so +2. Okay, +2 electrons. Okay, so well, at that time, of course, Rutherford didn't know that alpha particle consists of two protons and two neutrons, because neutron was discovered only only later in 1930. So neutron was discovered. Okay, so he only knew that it was that these particles appear during nuclear reactions found by how to say discovered by Marie Curie. So Marie Curie discovery gave Rutherford a source of alpha particles. So he used some radioactive substance which was the source of alpha particles. Maybe polonium, I don't know what source of alpha particles did Rutherford use, but it can easily be found if we read an article on Rutherford experiments. The idea is that this alpha particle sort of freely like leaped or came through these golden foils without being sort of hampered in their movement. But some of them sort of found an obstacle and were like reflected almost in the opposite direction. Okay, so but there were only few such particles that were this way reflected. So most of them came through this golden foil as if not so without any as if they found no obstacles, so freely. And well, the only explanation could be that that matter, or what we call atoms, are a kind of void in have some void in them. So the electrons, which were well, everybody understood that atoms are neutral, so electrons should be there. Otherwise, all elements would be electrically positive. So, but how are the electrons situated in atom? So the first model proposed by Thomson, was the English physicist, was that it's like a cake with dried with resin, or how to say izium. It's dried uh, well, um, I will look at that izium. I know only
Raisin.
raisin. Yes, I thought it was only in French, but it's also in English. Yes, so I think it's like raisin, maybe like that or not. Do you recognize this word? I will just try to Google it.
Yes.
It is dried grapes.
Yes, yes, it's
Well,
like that.
It is in
yes,
Sweet dried grapes.
it is one
yes,
of the
yes,
dried
yes, yes.
fruit.
Dried grapes. Yes. Okay. So if you take a cake with there, here or there are situated this raisin or dry grapes. Okay. So in the same way, Thomson thought that electrons are situated in the atom. So atom was like a how to say a field structure with some raisins electrons. Okay, but in that case, alpha particles couldn't go freely through matter because matter was sort of filled with these cakes, and they would find an obstacle and that will return where they were. But um, if so, Rutherford proposed new variant of atomic model, the so-called planetary model of atoms. Planetary model. So according to this model, electrons moved like on orbits uh, around this small positively charged nucleus. So here, this idea of atomic nucleus appeared for the first time. So atomic nucleus is positive and electrons are negative, so they move around this positively charged nucleus. Well, it seemed very beautiful and consistent with only one defect. Maybe Anshita knows what was the defect of this planetary model of atom proposed by Rutherford. Or maybe Mehdi knows. What was the defect of this planetary model?
The
So,
amount of electrons and protons which is required to present in that one model, like how many number of protons and
yes,
electrons
well,
are.
with numbers, this is not a big problem. So if, for example, if we take an atom of helium, there will be 2 electrons and 2 protons. Or at that time, there were no protons or neutrons because Rutherford didn't know about that. He only proposed that there was electrically positive nucleus and electrically negative electrons. So the total charge should be 0 because we know that atoms are neutral electrically. So with this, it's okay. What was the difficulty with this planetary model?
The difficulty is that the atoms are unstable.
Unstable, yes. Instability. Yes,
Yeah.
thank you, Angels. Here. This is instability. Why? Because electrons are moving around this positively charged nucleus. Every rotation, how to say, rotation movement, yes, is accelerated movement. So if a charge is accelerated in the electric field, he starts to emit light. This is how to say, this was proved by electrodynamics of James Clerk Maxwell equations. Maxwell.
It also has one more problem, um, as per the charged particles, it accelerated itself, like emitting and speeding up, like in which amount it should be rotate.
Yes, but rotational movement is accelerated movement. And
Mhm.
according to Maxwell equations and the laws of electrodynamics, every accelerated motion of charged particle in the electric field should lead to radioactive oh, sorry, electric electromagnetic radiation. So electron should emit electromagnetic radiation. But we see that no radiation comes from atoms. I mean, radiation, I mean electromagnetic waves, that we cannot observe any optical emission of light or any, well, if otherwise there would say night darkness in night would be impossible if because air is composed out of atoms, and if atoms emitted light, so there would be no darkness, but darkness exists. So something has to be changed somewhere, either in Maxwell's equations or in our idea of accelerated motion of electrons. So it was a big problem, which was not at first solved. So it was solved only by a pupil of Rutherford, a Danish physicist, Niels Bohr. You see, Bohr, Bohr. Do you know him? He's a Nobel laureate in physics, and he's one of the founders of so-called quantum mechanics. Well, what is that? So we now come to a very important first revolution, which is quantum mechanics. The second one will be Einstein's theory of relativity, but the first will be quantum mechanics. What is that? Quantum mechanics. So, yes, so
Said
what is classical mechanics? Classical mechanics means that there are so-called momentary speed, which is a derivative of, say, space by time, or better say, перемещение. Well, I think we can find it. Перемещение. Well, change of, well,
change of speed.
yes, but перемещение in Russian is
Maybe
in
moving.
English. Well, more, of course, I can say space, but I will prefer relocation, or you know, this if we take linear motion. So linear motion is that a body sort of transits from point A to point B. So this called like
Displacement.
Displacement, or well, travel also. So just movement. Okay, so when we take a derivative of this relocation, or sort of shift in in coordinates of this body, so we take a derivative by time, we find a so-called momentary speed, or in Russian it is мгновенная скорость. Okay, so speed is a derivative of well, speed or velocity. Speed is a derivative of, well, I can say of space by time. Okay, that's, well, I know it's not exact, of space by time. Okay, Maria, are you happy with this definition?
I
Yes,
think
but
okay.
Derivative of
Yes.
space by time. Okay. Well, uh, I say space. It's not good. We say relocation. Okay. Перемещение in Russian. Well, have you any idea? Or you prefer space
maybe you mean position, derivative
position
of
by time?
position
Yes.
by time. Yes.
Yes, but well, derivative of a position, I mean change of a position, okay?
Maybe
Yes.
In Russian, we have a
displacement.
very good displacement, yes, by
displacement, yes, it
time.
would be good.
Displacement, yes, okay. Displacement by time, okay, very good. So here is here's a displacement, yes. Let's call it displacement. So here is a classical mechanics, displacement by time. So time can be very, very small. Displacement can also be very small to infinity. So it can be even infinitely small. It doesn't matter. Infinitely small displacement in infinitely small time, but speed can be, well, not infinitely small. Two infinitely small, say, quantities are divided by are divided by each other, sort of, and the result of the division can be quite a normal, not infinitely small number. Okay, so here we have classical mechanics. Well, in atoms, Niels Bohr suggested the idea that this infinitely small times are not are only an approximation, but in reality, the action, well, you know what is action in classical mechanics? Um, it's a
Right?
action, yes?
Yeah,
It's
an act or a thing is moving.
Yes, but it is can be computed as mass multiplied by
And that's
displacement and multiplied by speed. So this all mass displace well, I will find, I cannot find the sign of multiplication sign. So mass multiplied by displacement and multiplied by speed. Okay, so all in all, this will be action. So there was in classical mechanics, there was the principle of the minimum of action. Um, Maybe you know this principle of the least action. It's called uh, law or principle, maybe a law of the least action. Least action. Do you know this law, a law of the least action? Uh, well, who knows? Maybe maybe Мария Зайчинока knows. Закон наименьшего действия, or principle.
Yeah, I was learned about it at the theoretical physics course, but I already forgot it a little.
Forgot it, but it is principle or law of the least action. Well, if you studied Landau-Lifshitz course of theoretical physics, the first volume is devoted to mechanics, classical mechanics, not quantum mechanics. And it starts from this principle of or law of the least action. So from this law of the least action follows the Lagrange equations. Lagrange equations. Maybe you have studied them or not. Lagrange equations. So this is
Yes,
classical
we've had
mechanics.
them.
Well, just an idea, you can just Google them, Lagrange equations. So these are or the law of the least action or the principle of the least action.
Lagrange equation is a system consist of the kinetic energy and the potential energy and the interaction between.
Yes. Well, yes, if you just look at the principle of the least action or the law of the least action, you will see how it is formulated. So it is, well, I suppose that you studied it already in, if you had a course of classical mechanics, okay? So if not, just follow my line of thought.
You can derive Lagrangian and Hamiltonian from this principle.
Yes, Hamiltonian is under the integer sign, okay? So it's the action is Hamiltonian, integer of Hamiltonian, and there's a like dt or little, how to say, превращение времени, okay? So, well, you see, or we can say energy multiplied by time, okay? So this is action, energy multiplied by time. So, well, principle of the least action presupposes that actions could be infinitely small because times can be infinitely small. So this is classical mechanics. What Niels Bohr sort of proposed? He proposed that there is a certain Planck constant h, which is he decided to take it as a quantum of action. Quantum, from this is born quantum mechanics, quantum of action. So H. Okay, now the conference will be ended, so this will be my last note here. Okay, so just see this quantum of action, and we'll start another conference. Yes, on the same link. Yes, Anshita.
Yes.
Okay. So yes, so in 1 minute we'll meet again. Okay.
Yeah.
Good.